Okay, great. Well, thanks everyone for tuning back in. And Alex Wein will tell us about low degree hardness of random optimization problems. Please, Alex, take it away.
Great. All right. Yeah, thanks a lot. And thanks to the organizers for having me here. So this is joint work with David Kamarnik and Akos Jagannath. So when I say random optimization problems, let me say what I mean by this. So by way of example, imagine I give you a random graph, like an Erdős-Rényi graph, and your goal is to find the largest clique that you can. Or maybe I give you a random KSAT formula, and your goal is to find a assignment that satisfies as many clauses as possible. Or maybe I give you a random degree P polynomial, and your goal is to find a point on the unit sphere in n dimensions that achieves the largest value possible. So in contrast to some other settings, here there is no planted solution. We're just looking at totally random data and finding, looking for the biggest or the best solution that we can find that just occurred by random chance. Okay, so for these types of problems, there's a few different things we might be interested in. First of all, we'd like to know what's the typical value of the global optimum with high probability. But we'd also like to know that if we restrict ourselves to polynomial time algorithms, what objective value can we reach? Okay, so I'll call these two thresholds opt and alg respectively. And the key question that I want to address is that sometimes we'll see there are cases where it seems to be computationally hard to reach a particular objective value, and we'd like to understand why. And particularly, we'd like to do this somehow in a unified way that applies to all kinds of different problems all at once. Okay, so this is sort of the motivation, and here's a more concrete example. So the maximum independent set problem in a random graph. So if we take the sparse Erdős-Rényi graph with n vertices and average degree d, we can ask, find a big independent set. So find a set of independent, meaning it's a set of vertices that has no edges in it, no edges among these vertices. Okay, and so the regime we're going to care about is where, imagine d is a large constant. Or in other words, I first take n to infinity with d fixed, and then after that I take d to infinity. And so in this scaling regime, we know the optimum, the maximum independent set is going to be a particular value, but algorithmically we only know how to find an independent set of half this size. And this is just by a simple greedy algorithm. And a number of years ago, Karp famously asked whether there is a better algorithm that can close this factor of 2. And we still don't know one. And in fact, we've started to realize maybe there just simply is not one. The first evidence for this was some kind of structural evidence saying that the cliques of size larger than alg cluster together in a way that makes it seem like certain algorithms should fail. More precisely, we now know that so-called local algorithms can achieve the value alg, but cannot do any better than that. So a local algorithm is basically something where each vertex only gets to look at its local neighborhood in the graph of, say, a constant radius and make some decision about whether it should be in the independent set or not, just by looking at its neighbors, along with some IID variables attached to each node. This is also called the factors of IID model. Okay, here's just a second example of a more continuous nature, where we look at basically maximizing a random degree P homogeneous polynomial over the sphere. So this is also called the spherical P-spin model. The input you get is basically this tensor of values, this y, right? Think of it as like n by n by n array of all the coefficients of your polynomial, and we want to just find a unit vector that maximizes this tensor form. Okay, and this is scaled in a way so that the true optimum, global optimum, is going to be some constant depending on p, and algorithmically, the value we know how to reach is some other constant, also depending on p. And these are strictly different, so long as p is bigger than 3. So for p equals 2, this is like a simple eigenvalue problem. But apart from that, we do not know how to find the global maximum. And again, there is some evidence that maybe we can't fundamentally. And this is, in this case, that this class of approximate message passing algorithms can achieve precisely this value alg, but cannot go beyond this. Okay, so what's missing here? Like I've shown you some results that are quite nice already. And so on a philosophical level, I'd like to address the question of how do we give the best evidence that there's no better algorithms? It's sort of beyond the current state of complexity theory to really prove there's no algorithms for this type of problem. So we want to give some kind of rigorous evidence, whatever this means exactly. And so prior work has ruled out certain classes of algorithms like the local methods or the AMP. But we should ask ourselves whether we expect these to be optimal. And maybe we'd be concerned a bit because, for instance, we know AMP is actually not optimal for a different problem called tensor PCA, which is really just the planted version of the p-spin model. So it's the p-spin model where you have kind of a planted signal. So maybe we're worried that it's not optimal for the non-planted version as well. And we'd also really would kind of like a unified framework for lower bounds and all these different problems. So the issue with local algorithms is they only really make sense for sparse graphs. And so this is not going to yield sort of a general purpose framework. And so here's sort of, the key idea that we propose here as a solution is that we can instead prove lower bounds against a larger class of algorithms, namely low degree polynomials. And this is a class of algorithms that contains local algorithms, contains AMP algorithms, contains the best known algorithms for tensor PCA, and various other things. And so, generally speaking, we sort of believe or conjecture that these are going to be an optimal class of algorithms among polynomial time algorithms. Okay, so what exactly do I mean by these low degree algorithms? So it's just low degree polynomials. So a multivariate polynomial that takes in m inputs and outputs. Or if you prefer, it's really a tuple of a few different polynomials, one for each output. And each one of these is real valued. And so we should think of the input here as just being whatever input we're given in our problem. So that could be an entire graph, like one variable for each edge. And the output we should imagine, for instance, is going to be maybe a vector, and we want it to be approximately the indicator vector of some independent set. And I said low degree, but I haven't really specified how much. You should imagine for this talk that low degree means like order of log n, where n is the dimension. I'll justify why a bit later. And so, why is this sort of an interesting class of algorithms? Well, one reason is that a bunch of different things can be captured by this. So for example, if I imagine my input is some matrix, here's a bunch of things I could do with low degree algorithms. One is power iteration. So starting with, say, the all ones vector, I could multiply by my matrix a bunch of times to get an approximation of the leading eigenvector. It turns out I could also do a constant number of rounds of approximate message passing, which is some kind of iterative scheme that I won't get into the details of. It turns out you can also do local algorithms. And crucially, you can also do some pre-transformation of your data. So I can, I don't have to do power iteration on the matrix I'm given. I can instead build some other matrix whose entries are, say, constant degree polynomials in the original data, and then do power iteration on that. So this lets me capture various, fancier spectral methods like the non-backtracking walk matrix or tensor unfolding and so on. And sort of the reason for the log n is that typically you need about log n rounds of power iteration if your matrix is well conditioned. Although there's also some situations where even a constant number of iterations is enough. Okay, so this is what I mean by a low degree algorithm. And so I guess I should say a bit more about where the motivation for this comes from. Really, the motivation for these low degree algorithms comes from a line of existing work for planted problems. So for problems that have a planted signal, say planted clique, sparse PCA, and so on, there's been this very influential line of work that's sort of introduced this concept of low degree algorithms. And it's now been shown that for a whole bunch of different problems, like the ones listed here, we know that low degree polynomials are as powerful as the best known polynomial time algorithms. Right, so this has two sides to it. In sort of the easy regime where we know an algorithm, then we also know that there's a low degree polynomial that works, typically some kind of spectral method. And on the other hand, in the conjectured hard regime, we're typically able to prove that no low degree polynomial succeeds. Right, so this gives sort of a nice framework for explaining what makes these problems easy for some regime of parameters and hard for another regime. And so the main idea of this work is to kind of take this whole theory that's been widely successful for planted problems and to see if we can do the same thing for non-planted problems. And hopefully use low degree polynomials as a kind of unified explanation for what makes all of these types of problems, either planted nor unplanted, what makes these hard in some cases and easy in others. Okay, yeah, feel free to stop me with any questions. So let me try to explain a bit what some of our actual results are. So this is just remembering the problem setup for this spherical p-spin model. So remember, there's some constant alg smaller than some other constant opt. And what we're able to show in this case is that no low degree polynomial can optimize all the way to the global maximum. Right, so there's some small absolute constant epsilon. And okay, I'll be a bit more formal now about what exactly does it mean for a polynomial to optimize this thing. So for technical reasons, where p needs to be even, and we're imagining a polynomial that takes your whole tensor as input and it outputs some vector. And the idea is that that vector is supposed to be like your v. And I'm saying that no low degree polynomial can succeed with high probability, where here's sort of the definition of success. So it needs to do two things to succeed. First of all, it needs to actually achieve a good value. And here is what I'm calling this h of v here. This is the Hamiltonian or the objective value. Right, so we want, in order for a polynomial to succeed, of course, the output needs to achieve a good objective function, but then also it needs to be like normalized in the approximately in the way that we wanted it to be for the problem. Okay, and so we're able to rule out any such algorithm, or we're able to rule out any such algorithm that succeeds with some explicit fairly high probability. This is sort of there for technical conditions, but really, in the easy regime, when we're below alg, we know you can succeed with even much higher than this probability, or with much smaller error probability. So this is sort of does not seem like too big of an issue.
One question.
Yeah.
Hey, so here the probability is for every polynomial, right? So, or is it like with this probability for no polynomial, this condition holds?
Let's see. So there is no polynomial that has the property that with very high probability it succeeds.
All right, makes sense. That's
Yeah,
what
sorry if this is written in a bit of a confusing way.
Makes sense. Yeah.
Yeah, good. Other questions? Okay, so let me, whoops. Talk now about the independent set, where here we can actually say something a bit stronger. So if you recall, there is these, the actual biggest independent set is twice as large as the biggest one we sort of know how to find, or the conjectured algorithmic threshold. So here we can actually get sort of the tight threshold, saying that no low-degree polynomial can get better than this threshold alg. And we also know the converse, that low-degree polynomials can get alg minus epsilon. And so we've sort of characterized the exact threshold where low-degree polynomials succeed, and it sort of coincides with the conjectured fundamental one. Again, I'll be a bit more formal about this. So here now we're thinking about polynomials that take in a graph, output a vector. The vector is sort of supposed to be an indicator vector for a big independent set. And again, no such polynomial can succeed with high probability, where succeed means a couple of different things. The first item is just saying, most of the output values should be either close to 0 or close to 1, since it's supposed to be an indicator vector. And then the second point is saying that if I take the ones where it's output 1, if I take those vertices, that should be approximately an independent set. So I have it a bit informal here, but essentially we allow for a small number of errors. So it's allowed to, mess up on a couple of vertices where the independence constraint is violated or something, but then we're just going to kind of throw these out. So we have sort of this definition is sort of a soft notion of success, and this is set up in a way so that low-degree polynomials can actually achieve this in the easy regime, like below alg. Okay. Any questions about this? So for the rest of the time, I want to tell you, how to actually prove such a thing. How do you prove that all low-degree polynomials fail at a task like this? And so let's first, recap what happens for the, the more classical setting of the planted problems. So low-degree polynomials have already been well studied in these planted problems. There's kind of two different types of planted problems you can imagine. There's detection, which is just about distinguishing, is there a planted signal versus is there not? And there's also the recovery problem, which is, actually finding the signal. Low-degree polynomials have been studied for both of these, and the proof techniques here turn out to boil down to actually just sort of straightforward linear algebra in some sense. Like there's a direct computation that, here it involves taking the likelihood ratio and projecting onto the space of low-degree polynomials. For the recovery, there's a bit of a trick you have to do first, but it then boils down also to kind of a direct computation. But that's sort of in contrast to what I'll say here. So for these random optimization problems, those type of techniques do not seem to work at all, and we need a totally different approach. And so what it will basically be is this. There's going to be two ingredients. The first one is that low-degree polynomials are stable in some sense. Roughly speaking, if you perturb the input a little bit, the output won't change too much in some sense. And the second one is some kind of structural property of the large independent sets in the random graph, or of more generally the space of solutions. So this is something called the overlap gap property and its generalizations. And so the versions of this we'll need are most directly inspired by this line of work here. Okay, so I'll get a bit more into the details now, unless there are more questions. So the first ingredient is this fact I said that low-degree polynomials are stable. Okay, so I'm going to focus on the independent set problem for the proof, because this one's a bit simpler, and we're able to prove a bit stronger things here. And so, okay, I'm going to imagine that y is just an IID Bernoulli variable. I'm eventually going to think of this as being the random Erdős-Rényi graph with one variable per edge. But for this slide, we don't need the graph structure, and we can just think of it as a bunch of Bernoullis. And I need to define something called the interpolation path. And so all this is basically that at step I of the path, I'm going to, oops, I don't seem to be drawing. At step I am going to resample, variable II. Or in other words, the ith edge of the graph is going to be resampled. So I start with just IID Bernoulli. At the first step, I resample the first, the first edge of the graph, and then I resample the second edge of the graph, and so on and so on. And here M is just going to be the total number of edges for us, the total number of variables, right? So I'm thinking of Y as having M components. All right. And here, for the graph, the edges are just listed in some arbitrary order that's kind of fixed ahead of time. Okay, so that's the interpolation path. And now I'm going to fix some low-degree polynomial. And I'm going to call a step of this path C bad if F's output changes a lot during that step. Right? If the output of F jumps suddenly at one step to the next, I'm going to say that step is bad. And how much to jump is sort of measured as compared to F's typical size or typical norm. Right? F is a vector valued. Okay, and here's the main result on stability that we're going to use. That if I draw this random, so F is fixed, but this path is drawn randomly. And I'm saying that the probability that there is no bad edge, is at least something. So this something is fairly small. This is just some non-trivial probability, but that will be enough for our purposes. So what it's basically saying is that with non-trivial probability over the path, F's output is kind of smooth. There's never a big jump. Okay. So this is a somewhat subtle sense in which low-degree polynomials are stable. You can notice that you can't hope to put high probability here because imagine, for instance, a dictator function. There's a decent chance that along this path, I'm going to flip the one important input bit, and that will cause the entire output to flip. But, there's going to be a non-trivial probability that I might just not flip that one important bit. Okay, so questions about this part of the result? So let me move on now to the second ingredient, which is this overlap gap property. Okay, so what does the overlap gap property say? So now I'm just, for now, imagine one graph. With high probability over one random graph, there do not exist a pair of independent sets with the following properties. Okay, so they're both independent sets. Individually, they are both large. Okay, so for a start, I'm going to prove a weaker result that doesn't get the sharp threshold, but gets this threshold instead. So we're trying to show that low-degree polynomials cannot find an independent set of larger than this value. And I'm going to use phi as this shorthand for the scale at which things happen. So if you remember, the opt is just 2 times phi, and alg is just phi. Okay, and this threshold is somewhere in the middle. So think of these as 2 large independent sets. So two large independent sets whose intersection is a very particular value, or within some small interval. Right? So it's saying that this never happens. So what's going on here? So 2 large independent sets, they're allowed to intersect a lot. They're allowed to be overlapping quite a bit. And they're also allowed to be, nearly disjoint or only overlapping a little bit. But what's never allowed to happen is sort of this particular intermediate case when their when their overlap is some precise value phi. Right? This never happens. For a typical random graph, you can never find 2 large independent sets that have this particular intermediate overlap. Okay, so morally speaking, this can be thought of saying that somehow the large independent sets separate into clusters. That for some given independent set, the other ones are either nearby, meaning they're kind of in the same cluster, or they're far away, meaning that they're kind of in different clusters. And the way to prove this is actually very simple and elegant. This is due to Gomarnik and Sudan, and it's just a first moment method. So all you do is compute the expected number of pairs ST that satisfy all these things. Right, this is just kind of a calculation you can do, and you can see that if you choose this intersection just right, that the expected number of these things will be tiny, will be exponentially small. And so we now know that with very high probability, the very high probability is even 1 minus, it's minus omega n. So exponentially small probability of this happening. And this will sort of be important because this exponentially small probability will it's important that this will be smaller than that non-trivial probability from the previous slide. Okay, is this overlap gap property clear? So that was actually kind of just a warm-up, and what we really need is a slightly more sophisticated version of this that's inspired by a couple of works, including some prior work by Gomarnik and Jagannath, where they basically realized that if you take a more sophisticated version of this OGP, which I'll describe now, this can somehow be used to rule out any sufficiently stable algorithm. Okay, so what is this ensemble OGP? So now I'm going to draw this this interpolation path like I described earlier, where you start with a random graph and then you resample the edges one by one. Right, so M is just the total number of edges. Each edge gets resampled exactly once, and the order is just some fixed but arbitrary order on the edges. Okay, and this more advanced OGP is now saying, even now there still does not exist 2 independent sets that are both large and both have that particular forbidden overlap. But now what's sort of different is that now S is allowed to be an independent set in one of these graphs, T is allowed to be an independent set in a possibly different graph. Right, so even if I allow S and T to come from 2 different graphs, you still can never find this pattern. Okay, and the proof is again sort of is the same, is just using the first moment method. And the bottleneck to proving this actually is just the case where I and J are equal. It's somehow only easier to show this when they come from different graphs. The reason is, imagine for instance, if the 2 graphs are just independent, you're basically any two independent sets, one from the first and one from the second, basically can never intersect very much, just because the graphs are so different. Okay, so is this definition clear? So now I will move on and tell you how to actually use this. Okay, so let's now put the two ingredients together. So I'll prove to you that no low-degree polynomial can achieve this objective value, right, which is somewhere in between alg and opt. So this is like a suboptimal result, but it will illustrate the main purpose, and I'll show you afterwards how to improve it to the optimal threshold. Okay, so what are we going to do? Well, let's sort of assume on the contrary that we had some polynomial that succeeds at finding these large independent sets. Okay, and what are we going to do? We're going to, imagine constructing these random correlated sequence of graphs where we resample a different edge at each step, like before. And what we're going to do is just apply, we have our function f. Let's just imagine applying f to each of them, right? And so in each case, we're going to get some independent set. And sort of fact number one that we need is that the first one, the one that comes from the first graph and the one that comes from the last graph, sort of have to be far apart. I've drawn them here as disjoint. Really they have to be just nearly disjoint. But why is this? This is just another fact you can show using the first moment method. Because these two graphs are actually just independent, right? We've resampled all the edges. Because the graphs are independent, there simply just cannot be, this new graph will not have any independent sets that correlate with whichever one you output here. Okay. And now recall that low-degree polynomials have this stability property. So with some non-trivial probability, the output of f is going to be stable, meaning that the independent set does not change too much at each step. Right, so the first one and then the next one can only change a little bit from there and so on. Right, so I can't change too many vertices at each step along this path. But now actually this contradicts the overlap gap property, right? Because if I need to sort of go from this first set to this far away set in sort of a continuous way, well, there must have been, some set along the way where the intersection with the original set is exactly this forbidden value phi, right? Or, approximate close enough to it. Right, and so by this sort of interpolation argument, we can find, we know that somewhere along this path, we're going to find a contradiction to the overlap gap property. Okay. Any questions? So that proves the result for this suboptimal threshold. Let me now tell you how to improve this. Okay, so how are we going to improve the threshold? So the idea from this is, at a high level is kind of inspired by work of Raman and Virag, who proved the analogous result for local algorithms. And the idea is instead of using this overlap gap property, right, this was a property about two different sets, we're going to have to use a more sophisticated property that involves more than two sets. So we're going to think about structural properties that involve a large number of different independent sets. Okay, so let me define exactly what is the key structural property we'll use. So again, like I've said a bunch of times, we're going to imagine sampling the same thing, start with a random graph, resample every edge. But here's actually a bit different. notice I'm going up to Lm instead of just m. So I'm actually just repeating the whole process L times, where L is some large constant. Right, so resample all the edges one by one, then in the next phase, resample all the edges again one by one, and repeat this L times. And given this whole sequence of different correlated graphs, there does not exist a sequence of sets such that what? Each one of them is an independent set in one of these random graphs. It gets to sort of choose which one. Independently, they're all big, where big now is really the correct target threshold that we're hoping for. And now this third property is sort of the key one. Okay, so what is this saying? This is saying like the number of new vertices that each set introduces needs to be in this particular interval. So it needs to be small, but not too small. Okay, this last property is only for k bigger than 1. Of course, the first set is going to introduce a bunch of new vertices, right? But let's say we have, a bunch of these sets so far. What this is saying is that, the next S sub k, whoops, somehow that disappeared. But if I have, say, these sets so far, the next independent set that I add to the sequence, the number of new vertices needs to be kind of this precise value. Okay, so quite small. So maybe I've drawn it too big in the picture there. But okay, this and so the theorem going along with the structural property is that it turns out by the first moment method that no such thing exists. That there does not exist a sequence of sets satisfying these things. And so how do we use this to rule out low-degree polynomials? Well, like before, we're going to sort of suppose we had a stable algorithm that finds these large independent sets. And we need to use this stable algorithm to construct an instance of the forbidden structure. And that would be a contradiction. Right, and so how would we use this stable algorithm to output a forbidden structure? Right, so it's actually not so difficult to see maybe. Right, the stable algorithm is sort of, as you modify the graph, the stable algorithm outputs some independent set that only changes gradually as you modify the graph. And so all we're going to do is basically just wait until this condition holds. Right, we'll take the first set automatically as our, the whatever comes from y0 will be our s0, and then we'll move along this interpolation path of graphs until we hit a set that introduces just the right number of new vertices, and then keep that one. And then keep going. Go again until we introduce another set that introduces the right number of new vertices, and keep that one, and so on. Right, and that will let us construct this. There's just one sort of caveat left, is that we need to make sure the algorithm isn't going to just stay in one place the whole time and never introduce any new vertices, right? And so we also need the fact that after m steps, right, after resampling the whole graph, the algorithm is forced to move to a new place because there just simply won't be any independent sets left that are in the same place. Okay, and that's sort of why we need to, that's why this L is the same as this L actually. Like the number of times we need to resample the whole graph is L, because at each of these phases, we're going to be guaranteed to pick up one set in order to construct our forbidden structure. Okay, so that's essentially the proof. Any questions about that? Okay, so I'll wrap up by giving a couple of comments. So I've mostly talked about the independent step problem here. For the p-spin problem, we can prove some similar things, but things are actually a bit more difficult there. You can't just use the first moment method to prove OGP. There's actually instead leverages some pretty sophisticated results from spin glass theory. And we don't currently know how to prove like the sharp results, getting exactly the correct threshold or the correct objective value. So that's one open question, is to find the exact objective value reachable by low degree algorithms for these spin glass problems. Another point is that we've ruled out low degree algorithms, but we've actually really ruled out any algorithm that's sufficiently stable in some sense. And this includes some other classes of things, like for the p-spin, it includes, for instance, this Langevin dynamics, which is some kind of a continuous time Markov chain. As long as you run it only for, say, a logarithmic number of iterations. And finally, I see this as being, part of a solution to a much larger meta question, which is that we have all these different heuristics for what makes problems hard, like the low degree method, but we also have things like sum of squares, statistical queries, overlap gap property, the cavity method, et cetera, and establishing, finding, rigorous connections between these things is sort of an interesting direction. And so here we've shown in some sense that a certain variant of the overlap gap property implies that something is low degree hard. And I'll leave you just with a list of some references for the low degree method more generally in a couple different settings. So both detection problems, recovery problems, and then what I talked about today was the last one, the optimization problems. Yeah, that's all. Thanks for your attention.
Thanks, Alex. There's a question here by Arsen Vasilian, who's asking if the stability property that you presented about low degree polynomials, if that statement was tight.
Oh yeah, that's a good point. Yeah, in terms of the error probability, or like the non-trivial probability there. Yeah, I think essentially it is tight. Like one example to maybe have in mind is, imagine P is just a half. And so I want to, to show this is tight, I want to construct some low degree polynomial for which, the probability really is quite close to this. And the polynomial I will take is just going to be like the product of the first, or rather the XOR, I guess, of the first D things. Or pick any D coordinates and take just the XOR of those. And so what's going on there? If the inputs, so this just takes values 0 and 1 as outputs. It's just a one single output. If the value ever switches from 0 to 1, then you lose. Then that's C bad. And so, the only way to not lose is if you never flip, and as like if going along this path, you never change any of these D coordinates. You're allowed to change the other n minus D, but not those D. And so the probability that you don't flip any of those D bits is basically going to be like, 1/2 to the D, which P to the D, which is basically what's here. Does this answer the question?
Yes. There's also, I think Ronen had a question. He had raised his hand.
Hey,
yeah.
Yeah. So I have two quick questions. I guess the first is your proof doesn't seem to rule out that there exists like two low degree polynomials, such that for most graphs, one of these low degree polynomials will point to a good independent set, because like you can kind of jump from one to the other. Can you kind of fix that and also say there doesn't exist, a small family of low degree polynomials such that, one of them has a good answer with high probability?
Okay, yeah, that's an interesting question. I haven't really thought about this. I mean, maybe one solution would be if you really had this family of polynomials, the hope was that I would hope I could combine these into one bigger polynomial that just always works. But maybe this is not obvious how to do this exactly. But yeah,
like it kind of seems like an obstacle to the proof, right? Because if you have two of them, you can kind of jump from one to the other in the middle of this interpolation path, and then.
Yeah, I agree with you. Right. I mean, I certainly don't know of any situation where an algorithm like this actually is known to help.
Sure. Yeah, it doesn't make sense.
Yeah, I just
wonder.
Yeah, I don't know how to rule out. Yeah, I don't know how to rule out such a thing.
And a second quick question: can you is there a quick way to explain how to implement the greedy local algorithm as a low degree polynomial?
Yeah, basically what you have to do is, right, so the first step is if you take the greedy algorithm, you can approximate that as a local algorithm by kind of looking at a large constant radius and sort of imagine running the local algorithm, or imagine running the greedy algorithm. But right, if you have this local algorithm where each vertex looks at a constant radius, you want to turn this into a low degree polynomial. It's essentially by by brute force enumerating all the possible neighborhoods that this one vertex could have, right? These neighborhoods are only like constant size. So with a constant degree polynomial, I can basically check, all the possible cases of what my neighborhood would be.
But then you still have to iterate this. So you're saying it's kind of closed under iterations, or?
You have to iterate this. What do you mean by iterate? Which
I just mean, it's just there's the loop of the greedy algorithm. I guess I'm just like also the local algorithm. Any local algorithm is kind of like you run a loop, I guess. So I mean, you have to enumerate the different neighborhoods, but then once you pick the next point, you have to do it again, I guess.
Okay. Yeah, I think I understand your point. Yeah, so what's really happening is that I'm approximating, so I'm not going to write the greedy algorithm. Yeah, the greedy algorithm is very sequential. I'm instead going to approximate it by a very parallel sort of thing, where each vertex looks at some large constant neighborhood, and its decision is just some function of what's happening in that neighborhood. And okay, every vertex does this in parallel.
That makes a lot of sense. Okay, thanks.
Sure.
There's also a couple of questions in the Q&A. I don't know. Can you see the questions, Alex? Or do you want me to read them out to you?
Oh yeah, I can see it. Technical barriers in ruling out low degree polynomials that work correctly with, say, constant probability. Yeah, that's a good question. Maybe both of these questions are kind of about the same. Yeah, so as is the current result is only ruling out polynomials that succeed with fairly high probability. Not just 1 minus the low of 1, but really, 1 minus n to the d or something. Really there's sort of a trade-off between the degree that you can rule out and the error probability. But essentially the technical barrier is that, first of all, there's this non-trivial probability coming from the stability lemma. And so the algorithm's failure probability needs to be smaller than that non-trivial probability in order to have a non-zero, right? The proof needs to have like a non-zero probability that you get a contradiction. So there's that, and there's also the issue that just I've union bounded over the algorithm succeeding at a bunch of different steps of this interpolation process. So yeah, I mean, it's a good question. It would be great to improve this error probability, but I don't really have ideas for how to do this.
Okay. Well, if there are more questions, the Gather Town will be open. And if not, we'll take a break until I think 11:30, where Dheeraj Nagaraj will tell us about phase transitions for detecting latent geometry in random graphs. Okay. So see you, everyone.